Hey everyone, so this is the second video in thermodynamics, all about the ideal gas law. So this is going to be a huge thing in this topic. All right, so some experiments came out. Now I don't know why chemistry always focused on this, but these are the three laws that we ended up finding out. So for example, one thing that they found was that when a system was set to a constant temperature, the pressure and volume were inversely related. Now, this was called Boyle's law, that pressure and volume were inversely related when the temperature was constant. Charles' law was saying that when we kept the pressure constant, we found that there was a direct relationship between volume and temperature. And then the Gay-Lussac's law was saying that when the volume was constant, the pressure and temperature were constant. Now, all three of these laws are just called the gas laws. And then what we ended up doing was we ended up combining them all into one single equation, which we call the ideal gas law. Now, going back, we ended up using the law, the one that said that the volume and temperature were directly related when the pressure is constant. Um, and this was used to find the absolute zero. That when they made a graph, they extrapolated the graphs, and they actually found that all the graphs, no matter what the material was, actually ended up crossing zero volume at the exact same time when the temperature was negative 273.15 degrees Celsius. And this is where absolute zero comes from. So again, they had a graph that looks like this. They backtracked it all the way down here, and wherever it crossed, that's what they called absolute zero. And then the temperature range basically just takes this zero line and shifts it over there. So the way you're going to convert between Kelvin and Celsius is using this equation. So your temperature in Celsius plus 273.15 gives us our temperature in Kelvin. Now, when you combine the three gas laws, you end up getting the ideal gas law, which is this: PV equals nRT. So P is pressure, V is volume, N stands for the number of moles, R is what's called the gas constant, and T is the temperature in Kelvin. In Kelvin. Now the thing is, the R term has different values depending on what units you use in here. Now typically, what I'm going to tell you is that I would like you to put pressure always in pascals, V volume always in meters cubed, and temperature always in Kelvin. When you do this, you're end up going to be using this term for R, 8.314 joules per mole Kelvin. Now, if on the other hand you use liters for volume and atmospheres for pressure, you're going to use this one, 0.0821. So again, you need to pay attention to the units and which one you're actually going to use. This one, where you're using calories, I believe you're using PSIs for pressure, and volume would be something like inch cubed, so cube inches or something. So that would end up giving you calories, something that you're probably never going to see. Um, Now, you're probably going to hear something called STP, which stands for standard temperature and pressure. It's essentially just a set value. So the standard temperature and pressure would be 0 degrees Celsius or 273 Kelvin. And pressure is 1 atmosphere or 1.013 times 10 to the fifth pascals. All right. So let's try and figure out what the volume of 1 mole of ideal gas is at STP. So pause the video, work on this stuff, and we'll go over in a second. All right. So what we're going to do is we're going to use the equation, the ideal gas law equation, solving for volume. We're going to set that equal to 1 mole and making sure that we use our pressure and temperature for at STP. And we end up getting that the volume is 22.4 times 10 to the negative 3 meters cubed, or 22.4 liters. Now, if you didn't know, this 10 to the negative 3 meters cubed is equivalent to a liter. So, use that in order to make your conversions. Um, this ends up being an extremely important volume. So this is true for any ideal gas. So if you have a gas set at STP, 1 mole will always be 22.4 liters. This makes it nice because when you're dealing with stuff at STP, you can find the number of moles by taking the volume and dividing it by the 22.4, or if you know how many moles you have, timesing it by 22.4 to figure out how much volume it'll end up covering at STP. So it's a pretty nice thing because we normally are dealing with stuff at STP, 0 degrees Celsius and atmospheric pressure. So yeah, definitely something you want to memorize. Here's the next question. You can pause the video, work on this yourself. We'll go over it in a second. All right. So they want to know how many moles of helium are in here. So the thing is, the volume is going to be used. We're going to use the equation 4/3 pi r cubed because we're assuming the balloon to be spherical, and we get that this is the volume of that balloon. Then what we're going to do is we have to figure out how much pressure and temperature there is. The pressure, we're going to take this atmospheric pressure and convert it into pascals. And then we're going to take the temperature and convert it to Kelvin. Now, if you wanted to, what you could have done is you could have taken this and converted this volume into liters. I think it would have been 24.4 liters, and then use the different value for R. But like I said, I prefer that you convert everything into meters and into pascals just to get into that habit. So using the ideal gas law, we end up getting that the number of moles is a little bit over 1 mole, which kind of makes sense. This is slightly above STP, and this is slightly above the volume of an ideal gas at STP. So it kind of makes sense that 1 mole would be the number of moles would be slightly above 1 mole. And then when we want to find the mass of the helium, so what we're going to do is we're going to take the molecular mass, which is 4 grams per mole. Now, if you're trying to figure out where this comes from, most likely it's been a while since you took chemistry, but the way you find the molecular mass is it's essentially just the number of protons and neutrons of that element, or the element number. And that number will always be the number of grams per mole of that element. So for example, helium has 2 protons and 2 neutrons. So it has 4 particles, so it's 4 grams per mole. Something like carbon, which is carbon 12, would have a molecular mass of 12 grams per mole. So just keep that in mind. It's going to make life easy if you do remember some of the numbers. You won't normally be asked something like doing something for trying to think of an obscure element like boron or argon, where not everyone will know what the molecular number is for that. Typically, it's going to be something common like hydrogen, helium, carbon, oxygen, nitrogen. Yeah, those would probably be the main ones. So we can actually rewrite this and say that, based off of these units, if I take the molecular mass and we times it by the number of moles, that will get us the mass. So take the 0.1066 moles, times it by the 4 grams per mole, and end up getting that the mass is 4.26 grams. But again, I always like to keep it in kilograms, so I'm going to convert it into this. All right. Here's the next question. Pause the video, work on this yourself. We'll go over it in a second. All right, so we want the number of moles of air at STP. Now, the thing is, they give us the volume of the room. So what we can do is actually use our little trick and say that we take the volume of the the material or the room and divide it by the number of the volume for 1 mole at SCP, and we end up getting that it's 1,700 moles. All right. Now, if we say something like 20% of air is oxygen and 80% is nitrogen, so this is the molecular mass of oxygen molecule, and this is the molecular mass of nitrogen molecule, um, and we want to figure out the mass, we can actually do it the same way. Take this and multiply it by the average molecular mass, and we get 50 kilograms. So air basically in this room is about 50 kilograms. All right, here's the next question. You can pause the video, work on this yourself, and we'll go over it in a second. All right, now some things to note before we go over this. So it's clear from here that we're going to do something with the ideal gas law because they give us pressure and they give us temperature. And we wanted to figure out what the new pressure is. So one thing to note is that this is a gauge pressure. If you remember from the fluid unit, I talked about how gauge pressure is essentially it's the amount extra pressure compared to the atmospheric pressure. So in the equation of the ideal gas law, the pressure in there is an absolute pressure, not a gauge pressure. So when they tell us the gauge pressure is this, what we actually have to do is convert that into absolute pressure first. So I take the 200 kilopascals and I add an additional 101 to it to get that the new pressure is 301 kilopascals. Same thing, I have to take the temperature and convert it into Kelvin. And then I also have to do it for the new temperature. And then what I can do is I can actually use the ideal gas law to set up a proportion from the initial pressure and temperature to the new pressure and temperature. And I end up getting this, that the new pressure is 333 kilopascals. Now the thing is, it wants to know the tire pressure now. So what I actually have to do, because this is absolute pressure, is I have to convert it back to gauge pressure by subtracting 101 to get 232. So the new tire pressure is actually 232 kilopascals, which basically means that the pressure ends up increasing by about 16%. So let's see. Now the main thing is why do we keep calling this an ideal gas law, and why do we keep saying the phrase for an ideal gas? Well, this is because of the fact that if you haven't realized by now, in science and especially in physics, we tend to always consider these ideal cases. Like in physics 125, you probably learned about dealing with stuff without dealing with friction. You know, you're shooting a ball in the air that's not affected by air friction. And we're dealing with cases where the gravitational force isn't changing by much. So it's just to make our lives easy. Now, for the ideal gas law, it's because what we're doing is we're ignoring certain effects. See, the thing is, this equation actually doesn't work at very high pressures, and it doesn't work when we get close to phase changes. So when like all of a sudden it starts getting close to the melting or boiling point, the ideal gas law kind of breaks down. Basically, what this is referring to is the idea that this is a good approximation of what's going on, but it's not really the greatest. Now, there actually is a better equation called the van der Waals equation, which makes corrections on things. Like, for example, according to ideal gas law, if we go all the way down to 0 degrees Kelvin, which is absolute zero, our volume should become zero. However, we know that we do have atoms that make up physical space. So technically, it's impossible to have zero volume. So that's one of the examples where this ideal gas law doesn't work, and instead, this new van der Waals equation will actually take into account the physical size of the molecules inside the gas, take into account the intermolecular forces between the gases as it gets closer to high pressures and these phase changes, and things like that. Um, Now, one thing that you've probably heard is learned about Avogadro's number if you've taken a chemistry course. Basically, the idea that equal volumes of gas at the same pressure, at the same temperature, end up containing the same number of molecules. The number of molecules in 1 mole of any ideal gas is equal to this Avogadro's number, which is 6.02 times 10 to the 23rd. Now, what we can do is we actually take the ideal gas law, replace the number of moles with the number of molecules divided by Avogadro's number to get this slightly altered equation. PV equals big N KT. Here, N, this big N, is referring to the number of molecules, and this K is actually referring to what's called the Boltzmann constant. Now, this has its own purpose. Typically, what this is usually used for is systems where you're dealing with a very small number of moles, like a small number of molecules. This is one where you would probably use this more often. Um, but yeah, you can use either of these equations. Like I said, you're more likely to be using the NRT rather than the NKT equation. But just wanted to show you that this is still in there. One hint, one tip, try to make sure that you're using lowercase and uppercase properly. I know there are some people that are always writing their words or writing letters in capital letters or always writing things in lowercase. Don't do that because then you're going to get these two ends confused. All right, here's the next question. You can pause the video, work on this yourself, and we'll go over it in a second. All right, so we want to figure out the mass of a hydrogen atom. So one hydrogen molecule is going to have, the molar mass is going to be this, 1 times 10 to the third kilograms per mole. So the mass is going to be taking this and dividing it by Avogadro's number. You can figure this out using unit analysis. A lot of times, if you're doing some sort of conversion, I actually do always recommend that you try to use unit analysis to figure it out. So for example, if I take kilograms per mole and divide by molecules per mole, the moles will cancel out and I'll get kilograms per molecule. And I get that. All right. So here's another question. You can pause the video, work on this yourself. We'll go over it in a second. All right, so we want to know how many molecules we breathe in during 1 liter of breath. So what we're going to do, there's a few things that we could do, but the whole thing is that we know that the number of molecules is going to be proportional to about 22.4 liters. This is Avogadro's number, of course. So we could set proportion that the number of moles that I'm breathing equal to over the Avogadro's number is equal to 1 liter over 22.4 liters, which is about this number of moles. What I'm going to do is then take this and multiply it by Avogadro's number, and I get this. All right. All right. So I'm pretty much going to skip a lot of this. Basically, what this is saying is that I had mentioned before that when we do temperature scales, we tend to pick 2 points. One of the points that they normally always try to use is something called the triple point. The triple point is if we take a graph of pressure and temperature, and we graph the phase that the material is in. So for example, when the temperature and pressure are on this side, it's in this solid phase. As we heat up the temperature, it'll either go into a liquid phase and then go into the vapor phase, or it could go straight into the vapor phase, depending on how much pressure. Or if the pressure is high enough, just never go into that liquid phase. Um, and then this point is actually the intersection of them. The triple point's usually referring to a, uh, a system where you actually have all three phases at the same time. So, for example, when you're in this location, you only have a solid phase. Once you go into this section, you're only liquid. But if you're right on this line, you actually have a little bit of solid and a little bit of liquid. So this is like the point where the where an ice cube is in the process of melting. So it's still got that solid ice, but all around it is a little bit of liquid water. Same thing here. If you're on this line, you have liquid, but you also have vapor boiling over. So at this point, you're going to have a little bit of solid, a little bit of liquid around it, and then also vapor around that. So that's what the triple point's referring to. This is just another graph that you can see. A little bit nicer looking. Uh, Again, triple points right there. I'm just going to skip a lot of this stuff. You can look at this later, but like I said, it's a lot of times used for temperature scales. All right, so that's pretty much it. So the two things that we talked about were the thermal expansion. We also related this to thermal stress, and we also talked about the ideal gas law. Again, make sure that your pressure, volume, and temperatures are all in the correct units. And make sure that units make sense with R and make sense with K. Now, one thing I didn't mention was I did say that you can choose the units for P and V to match R. However, you cannot do that for K. So, in order for you to be able to use this equation, pressure needs to be in pascals and volume needs to be in meters cubed. All right. So the homework for this chapter, chapter 17, is going to be due Friday. These are the questions that you're going to be working on. Like I said, I'm going to pick 3 from that. And if you have any questions, please let me know, and I'll see you later.